Hello, everybody, and welcome again to your channel, Thermal Engineering Concept and the Principle. This is Professor Ali Talad. I will introduce a briefing for some of the applications for heat conduction in a plane wall where there is heat generation. This episode will be under the title Mathematical Treatment of Heat Generation Physics in a Plane Wall and its first part. Here we will pass through the derivatives of the temperature distribution in a plane wall by using some of the boundary conditions. Thank you for your support and encouragement. And using your time in such applications and such topic in heat transfer and energy in the field of mathematical treatment of these topics. And let us go to the objectives of the present episode. The objectives of the present video are related to the one-dimensional heat transfer by conduction in a plane wall under the steady state conditions. We will use some of the boundary conditions to find the temperature distribution inside the wall such as fixed walls temperatures, where both sides have different temperatures, and when these sides of the wall have equal temperatures, uh, and the adiabatic boundary condition, where an insulated surface is considered, uh, and then we will approach the logger. Can we reduce the general form of the uh, three-dimensional heat conduction in um, solid material? One of the most interesting forms of this equation is the one-dimensional steady-state heat transfer. And this form of equation has many applications in industry, or we may minimize the effect of other dimensions, so we will consider the heat process to occur in one direction. The general form, as has been presented by equation number 2. How can we reduce this equation to the form of one dimension? As shown in this figure, we have the faces, and we may consider it as element with a thickness of L. And if we ignore the effect of y direction, then that means partial square t with respect to y square will vanish and approaches 0. And in the z direction as well, we may have um, partial square t with respect to z square equal to 0. And that will yield um, a form of equation where can be applied in the one dimensional form, heat conduction with heat generation. And this is called the transient form, which is represented by equation 2.1, partial square t with respect to x square plus q dot divided by k equal to 1 divided by alpha partial t with respect to tau. And this form of equation is a general form and can be used even for the case where there is no heat generation. So for steady state, you will get the right-hand side will go to zero. That is, the temperature doesn't change with time. So we have partial T with respect to tau is equal to zero. And the final form will be d squared T by x squared plus Q dot divided by K equal to zero. This is the general form for steady state conduction heat transfer with heat generation. To use this equation and to find a solution, we need to execute an integration. The first integration will give us q dt by dx plus q dot divided by kx equal to 0. And if we conduct the second integration, we will get t of x as a function of x plus q dot divided by k x squared divided by 2 equal to c1x plus c2. This is a magic equation where it is used in the one-dimensional heat transfer with heat generation and can be used regardless of the boundary conditions. So I will call this equation a magic equation. Now let us have a case study where we have fixed walls temperatures on both sides. And for example, we have a wall shown in this figure with one-dimensional form, and it has Q dot generated per unit volume inside this body, and thickness L with a boundary conditions as shown in this photo that we have the fixed temperatures on both sides. If we go back to our magic equation, T of x, the point or the object is how to find the constants C1 and C2. And usually for this type of equation, we will need two boundary conditions. This is another form just to show schematically how heat transfer is occurred through this wall. And we have Q usually is perpendicular to the surface area of the wall. The first boundary condition we have when x equal to 0, then t as 0 equal to t1. This is boundary condition number 1. And the second one on the other face of the wall, where x equal to L, then we have the temperature equal to T2. Applying boundary condition number 1 and the magic equation number 4 will yield C2 equal to T1. That means you have to substitute for the value of x as 0, and then the temperature is T1, then this will yield C2 equal to T1. And if we apply boundary condition number 2 for the same equation, that will, with the C2 equal to T1, then we will get T1 equal to T2 minus T1 divided by L plus Q dot L divided by 2, which is represented by equation number 9. If we substitute these values of C1 and C2 in the general form of equation 4, then the temperature distribution is shown T of x plus Q dot divided by K x squared divided by 2 equal to the right-hand side in terms of the given values of T1, T2, and other properties of the wall. So the final form is represented by equation 11. We have to prove that this equation is right, is correct. So we will use when x equal to 0, then T of x equal, if we substitute x in equation 11, that will give us the first term on the right hand side goes to 0, and x, the second term will go to 0. Then the temperature T of x equal to T1, which is the same as the boundary condition number 1. And for the second boundary condition, when x equal to L, if we substitute that, then we will get T sub x equal to T2, which is the same value as used in the boundary conditions. Now, let us consider the case where we have constant uh, temperatures at the walls. If we consider the wall, which is shown in this figure, uh, is exposed to heat transfer in one-dimensional form with a heat generation Q dot watt per meter cube with a thickness L, and we want to derive an expression for the temperature distribution through this wall, uh, and we need to find the position of maximum temperature. Solution for this equation. We have the magic equation, which represents by uh, equation 4, and we need two boundary conditions to get the final form of temperature distribution. We have T1 equal to T2, which equal to T, as shown in the figure. Thus, we have a constant temperature on both sides. And such conditions are even available in industry. Uh, for example, a wall is exposed to environment. Then we will have heat transfer to the environment, and the temperature uh, uh, is constant on both sides wherever there is a heat generation per unit volume as a uniform value. Then we have two boundary conditions at x equal to 0 and x equal to L. That is t equal to t of x equal to t. Applying boundary condition 1 in equation 4 uh, and substitute the value of x as 0, then we will get C2 equal to t. And if we apply boundary condition number 2 together with the constant C2 equal to T in equation 4, then that will produce a general form of C1 in terms of Q dot divided by K times L divided by 2 as shown in equation number 9. So if we rearrange and substitute the values of C1 and C2 in equation 4, then we will get the final form T of x equal to Q dot divided by 2K times Lx minus x squared plus T. This is the general form of the equation. How can we verify this form? If we substitute the x equal to 0 in equation number 11, then the temperature T as 0 equal to T. And similarly, if we substitute x equal to L in equation 11, then we will get the temperature T at L equal to T. Then equation 11 is correct and right to represent the form of temperature distribution. So the second part of this example, how to find the position of T max. And to get that, we should take the derivative, the first derivative dt of x by dx equal and equate that to 0. And from that, we will get x equal to L divided by 2. And that means we have the maximum temperature will be positioned at the center. This is because we have constant temperatures on both sides of the wall. Case study. For the cases where we have equal temperatures on both sides of the wall, of course, we have passed through such boundary condition uh, in a rational way. Now, let us consider a complete example for the wall where it is exposed to environment or another thermal fluid where we can uh, keep the temperature on both sides uh, way that they are constant. Uh, we may go to the general form of the one-dimensional heat transfer by conduction with heat generation, equation number 3, as it has been derived previously. And we may uh, obtain the uh, temperature distribution in the form shown q dot divided by 2k times Lx minus x squared plus t. And this form of equation, of course, has been obtained from a previous episode. And to get the maximum temperature of the in the wall, we have to take the first derivative and equate that to 0, dt by dx equal to 0. And if we, from equation 3 or the result of equation 3, if we uh, derive the value for dt by dx, then it will equal to q dot divided by 2k L minus q dot divided by k times x equal to 0. And from this equation, we may get a form for the uh, x as equal to L divided by 2. And this is the final answer for the present example. Let's introduce another boundary condition which can be existed in some industrial applications. That is the adiabatic boundary condition. If we consider a wall uh, as shown in this figure, with one side is insulated, perfect insulation, so that will tell us Q equal to 0 at this side, and the other side is exposed, for example, to a convective fluid at temperature T and H heat transfer coefficient, and its temperature T sub W. And let us assume that we have a heat generation per unit volume as a Q dot. And the point that how can we find the temperature distribution in such application? The solution for this example, if we go back to equation number 3, d squared t by dx squared plus q dot over k equal to 0, which is the general form of steady state one-dimensional heat conduction with heat generation. And again, the magic equation that is equation number 4. P sub x equal to q dot x squared divided by 2k equal to c1x plus c2. To solve this equation, we need two boundary conditions. The first one is isolated or insulated wall minus k a dt by dx equal to 0, and at x equal to 0 then we have dt by dx equal to 0. That is a perfect adiabatic surface. And if we apply dt by dx in a form derived from equation 4, then we will get dt by dx plus q dot divided by k x equal to c1, and if we substitute the value of x equal to 0, then with dt by dx equal to 0, then that produces c1 equal to 0. We have, if we substitute this value of c1 in equation 4, then we will end with a form of equation 5, t of x equal to q dot divided by k x squared divided by 2 equal to c2. Then we will need another boundary condition, and let us take at x equal to L, then t equal to t sub w. T sub w, if we substitute that in equation number 5, then we will end with t sub w plus a q dot divided by k, L squared divided by 2 equal to c2. Substitute these values in the form of equation 5, then we will get the final temperature distribution as T of x equal to q dot over k x squared over 2 equal to T sub w q dot divided by k L squared divided by 2. And rearranging this form, we will get T of x as equal to tw plus q dot divided by 2k L squared minus x squared, which represents the final form or the answer for our equation in this example. That is represents the temperature distribution in this wall. To get a verification for this form, at x equal to 0, if we substitute that in the form of equation number 6, then we will get a t equal to t max equal to tw plus q dot L squared divided by 2k. And at x equal to L, then this equation, I mean equation number 6, will produce t sub x equal to t sub w. The final part of the present video is related to the closure of the present episode that we derived with the one-dimensional heat conduction in a plane wall with some of the boundary conditions that they are used in industrial applications. Here we have derived the final form for the temperature distribution, where fixed temperatures or equal temperatures of the walls are considered for the plane wall, and at the same time we treated the adiabatic boundary condition. And here we are. There are some useful resources that may be used to help you to enrich your knowledge about this topic. It is found in a PDF with a link in the description box. Thank you for watching, and I hope that you will subscribe and share the information with your friends to achieve the most important objectives of the creation of the present channel. And thank you for watching, and see you next time. Bye bye.